Good morning, good afternoon. I am Ana Flávia Nogueira, Director of the Center for Innovation on New Energies. This is a center that is sponsored by Shell and São Paulo Science Foundation Agency, FAPESP. So before we start our Cine webinar today, I would like to call your attention to the all attendees that our annual event is approaching. It's going to be in 1 month, in a couple of days, in October 18 and 19. So our annual event this year is going to be in person after the pandemic. It's a free event, but we have a limited spots for attendees. So please, if you're interested in joining us 2 days here in Campinas, please go to our website, www.cine.org.br, and sign for our annual event. Okay, we have a great, very nice scientific program that includes the 4 programs at Cine. So it's a great pleasure to invite our speakers of today, Professor Thomas Anthopoulos. Thomas is really far away. Thomas is now in Saudi Arabia. What time is it for you, Thomas?
It's 5 o'clock in the afternoon.
Oh, it's 5 o'clock. Not too bad. So thank you for joining us today here at our Cine webinar. So let me say some few words about Thomas. Thomas is Professor of Material Science Engineer at King Abdullah University of Science and Technology, that we know for KAUST, in Saudi Arabia. He received his bachelor and PhD degrees from Staffordshire University in UK. Then Thomas spent 2 years at University of St Andrews, a very lovely place in Scotland, when he worked on organic light-emitting diodes before joining Philips Research Laboratories in the Netherlands to focus on printable microelectronics. From 2006 and 2017, Thomas held the faculty positions at Imperial College and in London. Well, also I was a fellow for Imperial, so it's nice that we never have a chance to work together, Thomas, because I was at Imperial much before you, was it during 2002. But then now Thomas has his position now as a full professor in experimental physics in the KAUST. So it's a really pleasure, Thomas, to have you here, and I hope to see you soon in Boston in November. The stage is yours, Thomas.
Thank you, Ana Flavia, for the very kind words and for inviting me to present in your seminar series. As you can see from the title of my talk, I will talk a little bit about solar cells. It's not often that I am invited to give talks about solar cells. It's been only part of my activity, a core activity, I should say, the last 5 years since becoming a member of the KAUST Solar Center. The center is quite large. We are 150 people altogether, or maybe more, focusing on all type of solar cell activities. And today I'm going to talk a little bit about my group's work in collaboration with a number of people from within KAUST, but also from around the world. Why you're interested? I show this famous plot of world energy consumption. As you can see at the very top here, we see only a minute contribution from renewables. Also, although this chart is a bit outdated, it's a few years old, it captures the reality. And if we zoom into this renewable section, we will find PVs among hydro, wind, and other renewables. Now, the PV technologies, photovoltaic technologies, can be split themselves into 3 generations. First generation, classic crystalline silicon is essentially what dominates the market of high-performance commercial products. Then we have the second generation. We have a number of different materials, cadmium telluride, SiGs listed there. Amorphous silicon is also part of the second generation, allows these thin film processing capabilities that first generation single crystalline silicon is not. And of course, we have the very popular nowadays third generation, which this encompasses organics, perovskite, dye-sensitized quantum dots, and a number of other technologies. And the work I've been doing is focusing entirely on these third generation type technologies. And I will talk a little bit about that. Why we're interested? Of course, we are now having first generation silicon technologies. This is, or not only, but a summary of those are captured in this very famous NREL chart, where we see essentially the cell efficiency as a function of year. And if we focus in silicon, single cell silicon, you will see that we are now actually pushing the limits of the very efficient products in the market. OPVs and perovskites are lagging a little bit behind. Perovskites are really, really efficient, but there's, of course, they come with their own problems. My group is also working on perovskite PVs, and but today I'm not going to be talking about that part of the work. OPVs instead has been kind of attracting a lot of attention 20 years ago. We've seen an increased step change over every 5 years or so. And the last 5 years, we've seen also a quantum leap in terms of performance. We've seen cells jumping from around 10% to now very close or over 20% for some of the more complex device architectures. And this is an interesting development because my group, as well as other groups around the world, have predicted that the efficiency can be potentially much higher, potentially even higher than 25% power conversion efficiency, if we can optimize all aspects of the cells. And who knows how far we can push it. Just to give you an idea, I'm also working on technologies beyond solar cells, which is even more interesting, but so far we don't have any successful results to report. That will be the topic of another discussion, hopefully in the future. Why you were interested in these emerging forms of PV technologies, this can be actually kind of emerges if you do an analysis of existing commercial products based on silicon. So if we see silicon installations on a residential level, you will realize and actually separate the different contributors to the overall cost over the years. You will see now we are somewhere here. And if we split the cost of module, is the gray bit here you see only a fraction of that total cost is due to the actual production cost associated with the silicon. All the rest are soft costs, installation, hardware, the inverter circuit we're going to be using, an additional cost associated with that. That balance is disturbed if we move from residential to utility scale, really large scale installation for the grid, where we essentially see the module cost becomes relevant and comparable with the remaining of the cost or even greater. So this is a bit of a problem because there's not much we can do in terms of the installations, but we can do a lot on coming up with new and innovative ways of incorporating these emerging forms of PV technologies with existing infrastructure. And one of those is essentially building integrated PV solutions. And this is just a bunch of images I found from the web that capture exactly this idea. And I'm sure all of you are familiar with these kind of installations. We actually start seeing them around new buildings. It's an existing ongoing project, and we see more and more deployment of such technologies to new architectures. And this is, of course, a very popular example for the organic photovoltaic community. It comes from Mature in Brazil, and the installation of the rooftop of all these organic photovoltaic cells, and just demonstrate the potential of these emerging technologies. However, these technologies don't come without any problem. There is still a lot of techno-economic challenges that need to be addressed, and this is what we're trying to do in my group. We also have emerging markets, and one of these is the Internet of Things device ecosystem. We're now feeling, or there is a genuine need for power sources that power distributed network of electronic nodes, such as gas sensors that are interconnected to the Internet of Things ecosystem, humidity sensors, hydrogen sensors maybe in the future, maybe smart windows, and a lot of these distributed smart devices. How to power these devices is not clear yet. there's no single solution that tick all the boxes. And potentially this third generation photovoltaic technologies can deliver something that is not yet been satisfied by existing technologies. And this is a good example of the cost of a few integrated PV power products as a function of year. We've seen, and we are all familiar with calculators incorporating a silicon solar cell. I've been using this since I was a kid, and this cost has been dropping. But as you can see, the indoor PV market size is increasing exponentially, and a lot of opportunities will be created, and part of these opportunities will come from the Internet of Things device ecosystems. Why organic and other third generation technologies are interesting? It's simply because they are efficient, inexpensive to manufacture, potentially upscalable manufacturing, therefore potentially beneficial in terms of cost, but also efficiency. So this is some indoor PV cell efficiencies based on different different lighting, LED, but also fluorescent lights. And as we can see, perovskites, organics, and dye-systized solar cells are actually some of the most efficient ones. Of course, OPV offers a lot of tunability in terms of material options. The same one can argue with perovskites, but what I want to highlight here that all of these families of PV technologies are valid contenders, and I think they will be soon providing solution to this genuine need of identifying suitable power sources. Another big advantage associated with organic photovoltaics in particular is the carbon emissions. If we now look at the gram of a CO2 equivalent per kilowatt hour for the various PV technologies, we start from monolithic silicon to multi-silicon, multicrystalline silicon, CIGS, cadmium telluride, and here is a product from Heliotech, this Heliosol. Essentially, this is taken from this white paper from Heliotech, a very interesting paper that I highly recommend it for those of you who haven't seen it to really download it and read it, and have predicted that this carbon emission for one of their products can be as low as 8 grams of CO2 equivalent per kilowatt hour. This is pretty low and is actually lower than most of the competing technologies. Of course, these numbers, I had discussion with people that may argue against them. You have to be taken with a pinch of salt, but clearly highlight the potential of organic PV. And it's only not only that. If you look and study that paper, there's also another comparison. We essentially highlight the potential of OPV to deliver some of the lowest carbon emissions among the various energy sources, including the lowest of the low, which is the hydropower. So this is another indication that these emerging forms of PV are really here to stay. And the question is, how do we really make it from a scientific curiosity to early stage products to a commercial reality and success? And this another important parameter, which I highlighted here. This is from a report I put it together from based on published data and sources from the internet. And the striking value here is this energy payback time for the various technologies. And we have organics here with the various assumptions made, 5 to 10% efficiency, lifetime of over 10 years, and the emission on that range. We have essentially an energy payback time of a few months to a year or so, much, much shorter than most of the other competing technologies. This is kind of nothing short of stunning to see that if we can really do that, then a lot around the PV market can be changed. How we view these PV technologies, we soon realize that we can't really just simply compare OPV or other third generation technologies, just existing silicon-based technology. We have to start thinking differently. And I think this is exactly where we're going to be in a few years in the future. So what do we do in my group to address the various issues? We work across the entire cell. We don't build or scale up the production of the cells, but we do work on the active layers. We are actually having an extensive collaboration and partnership with a number of chemists around the world. We also work on ways of identifying existing bulk heterojunction materials and addressing fundamental limitations, like, for example, how do we overcome the associated losses, like for example, associated with the excitonic behavior of these materials. We also work on interlayer materials, and I will spend a good part of my talk here talking about these interlayer materials and how important they are in device efficiency optimization and operation stability. So what do we need from a device? We need essentially an organic photovoltaic or any other photovoltaic to have a photoactive layer. But then we often, in these third generation technologies, we combine this photoactive layer with suitable hole transport layers and electron transport layers that are responsible for extracting the holes and electrons, respectively, from the device without any losses. So there is a critical physical characteristics of these layers should be versatile in terms of their processing. The simpler there is, the more economical, viable will become. Appropriate surface energetics, so we can actually print on top of each other without dissolving them. So as an aspect of orthogonality, they should be optically transparent, come with a suitable energetic, so you can extract the holes and electrons without any losses, but also to block minority carriers. For example, in the hole transport layer, we would like the layer to actually block minority carriers on that side of the device, which is electrons, and the vice versa for the ETL side to block holes. Therefore, there's a number of important attributes that need to come together. And on top of that, we need these charge transporting layers to be exhibiting high electrical conductivity, so there is no resistive losses associated with the charge extraction. So this is the outline of my talk. I just tried to go through some of the important work that my group did over the past 5 years or so, starting with the use of copper thiocyanate. This is an inorganic wide band gap semiconductor that can be solution processed and is a p-type, hole transporting in character. Then I moved to some interlayer technologies, which are related to low dimensional materials. And I will finish with some multifunctional additives, essentially dopants that we have been introducing into the bulk heterojunction of our devices to improve the overall performance of our OPVs, as well as their operating stability. So let's start with the copper thiocyanate. This is an inorganic molecule. Many of you perhaps haven't seen that. It was the same for me probably 12 years ago when I came across it. And it was Brian O'Regan, the inventor of the Grätzel solar cell, that introduced me to this material. I thought he was talking about copper thiocyanate, the dye, but he was actually talking about copper thiocyanine. It's a quasi-molecular system, essentially, and has a mixed character where it comes down to the energetics. So the valence band is dominated by the copper 3D orbitals hybridized with the sulfur, and essentially it's a layer system. And the conduction band minimum is actually mostly dominated by the cyanide character. Therefore, there is a huge asymmetry in the charge transport, but also in the character of it. So the end result of this material is that it's a wide band gap. It's over 3.5 electron volts, so it's optically transparent. And it's a p-type in character. It's actually an intrinsic p-type material. And it's highly polycrystalline when you solution process from suitable solvents. So this was the first data we got that proved that is actually a p-type semiconductor, is a transistor data. What we see here is the channel current versus the gate voltage we have used. And we see clear hole accumulation and depletion, which indicates a kind of an intrinsic p-type conductivity within that material. Since then, we've been able to analyze, of course, the optical transparency. And the first material we compared copper thiocyanate against was the standard commercial available PEDOT-PSS, which is a standard hole extracting interlayer for most of the OPV technologies and devices found in the literature today. And as you can see here, this is a transmission across the film, through the film. See, the PEDOT-PSS is particularly bad when it comes down to near infrared part of the electromagnetic spectrum. We see there is a lot of absorption, which essentially leads to power loss spectra. So if we compare the copper thiocyanate as an HCl layer and PEDOT-PSS as an HCl layer, essentially by replacing PEDOT-PSS with copper, we can actually gain back all this power loss spectra, which is easily a few percent at least from a device. So this is exactly what we've done. This was the first experiments we published at the time, and this is already now over 7 years ago, where essentially we took the same bulk heterojunction system, a P3HT ICBA in this case, we replaced PSL with copper thiocyanate, and because we can have actually higher optical absorption, essentially minimizing the parasitic absorption associated with PSS, we're able now to obtain a higher EQE spectra and essentially a higher short circuit current, as you can see here. And overall, the power conversion efficiency was much higher. We were able to overcome the difficulties associated also using sulfur-based solvents like DES, or everything I've been showing you so far was based on copper thiocyanate process from DES, and we use aqueous ammonia. So essentially, the moment you dissolve it there, the copper ion dissociate. You see this coloration of the solution to blue, which is classic for copper ions in the liquid. We made transistors. We saw that the aqueous ammonia processed copper thiocyanate behaves better. It's actually end up with a higher quality layers as compared to DES processed copper thiocyanate. We see a higher mobility from transistor measurements. And when we make actually the devices, we see that the ammonia process, aqueous ammonia processed devices were yielding higher power conversion efficiency than those based on DES processed copper thiocyanate OPVs. And we're able to make also inverted cells, as well as extend this application to perovskite PVs. I think this data was at the time one of the highest efficiencies for a copper thiocyanate or a kind of an inverted cell, if I recall correctly. And this just demonstrated not only the potential of copper thiocyanate, but also the universality applicable to organics, but also to perovskites. Since then, and very recently, actually, just a few weeks back, we learned how to, essentially, we published a study where we show how one can actually improve the electronic properties of copper thiocyanate by simple chlorine doping. Essentially, you take chlorine gas in one of the standard systems we use for etching. We introduce our copper thiocyanate layers on a substrate for a few tenths of seconds, and essentially we see a huge doping effect emerging. Essentially, the chlorine doped copper thiocyanate exhibit much higher hole concentration, essentially eliminates a lot of the problems we have with deficiency or defects in the layer. So this is a classic example what happens if you don't have an optimized copper thiocyanate, and the moment you take the same layer and expose it to chlorine, then you eliminate all this S shape, which is associated with contact resistant systems, which is often found with the latest NFA systems. With copper thiocyanate, we realize it's not the best HDL for the latest NFA systems, but once you dope it, this is not anymore a major issue. We also use the same approach, essentially the chlorine-doped copper thiocyanate, and applied also to perovskite. And if you are interested in this work, please refer to this paper that just appeared online. And what we have done here, we use the pure copper thiocyanate. You see we're losing voltage, but also a little bit of current. And the moment we introduce the chlorine-doped copper thiocyanate, which is a stable form of doping, this is a kind of a surprising to us how well this copper thiocyanate layer were doped. We can gain voltage, and as a result, we can actually push now the single cell efficiency to over 20%. I know this is quite a well-established number from around the world, but in our laboratory, it's not easy to push it over 19%. So clearly, the ability to have a good whole transport layer makes a difference in our perovskite devices. What we also been able to do with this copper thiocyanate in the past is to take it and radically rethink how we build devices and actually use it as a fundamental building block for understanding basic processes. So we took one of the bulk heterojunction devices and we thought, okay, could we eliminate the PSS and the actual donor polymer, and instead using copper thiocyanate together with an acceptor material like a PCBM, a C70 PCBM, and see whether we can make a single photoactive material solar cells. So we went ahead and we used fullerenes because the fullerene derivatives we know are perfectly electron and hole transporting symmetric. It's essentially exhibit the same hole and electron mobilities, and therefore are materials that actually can photogenerate and you can photoexcite them, create these charges, and essentially try to separate them. So what we've done, we took copper thiocyanate, we deposit on the top a pristine layer of PCBM and created bilayer devices. And depending the thickness of that PCBM layer, we could get actually up to 1% efficient devices. We're able to improve it dramatically by taking this copper thiocyanate and the PCBM, but now within the PCBM, we also introduced a small amount of copper thiocyanate. And we're able to make actually PCBM-only devices with a 5.4% power conversion efficiency. Why it was so higher? Simply because we increased this interfacial area. So when we analyzed our devices, we saw essentially this spontaneous formation of this mesostructure type of nanowires of copper thiocyanate embedded within the dark areas, which is the actual fullerene. And as a result, we had a very nice interpenetrating network of a P-type material accepting the holes, but does not really donate any electrons. And all the photoexcitation, the charge generation is happening within the actual fullerene. So it was, to my knowledge, one of the or maybe the highest efficiency fullerene-only based solar cells. But that demonstrated the power of copper thiocyanate. We also been able to use it for basic studies. Again, we went back to the bilayer systems, copper thiocyanate, which is fully transparent, doesn't absorb any light relevant to the solar spectrum. And then we deposit an acceptor layer with different thickness. Many different acceptors have been tested, and a handful of those are shown here. I think we tested over 10 acceptor materials at the time. And then what we've done, we were measuring the external quantum efficiency of the device as a function of the layer thickness of that NFA, the non-fullerene acceptor. And we could actually resolve that peak performance somewhere at the critical thickness. And with the aid of modeling, we're able to extract the external diffusion length in these systems. And the summary of those external diffusion length appear here. This is actually most of our results extracted from this study. And as you can see, from PCBM, we extracted a number around 10 nanometers. This is not surprising because similar numbers been reported many times in the literature. But what was very intriguing to us, it was that a lot of the NFAs exhibited quite a high, long external diffusion length. IT4F, for example, reached up to 47 nanometers, which was perhaps one of the reasons why these NFAs are also very good and high to produce high performance OPVs. Switching gears now and in a way moving away from the copper thiocyanate and essentially focusing a little bit more on a new and emerging materials suitable for hot transporting layers. Copper thiocyanate, as I've shown you, is very versatile, but comes with its own problem. For example, processing it, the need for annealing it, and the need for essentially making it compatible with a number of different photoactive systems presents numerous problems. So while we were working with the copper thiocyanate, we'll be also exploring simultaneously a number of other materials, and I will highlight a few families here. So what I call low dimensional here is essentially materials which are very thin in terms of the layer thickness we're trying to form. One of these systems, and this little video we have recorded when this paper was published in Advanced Materials, relates to the exfoliated two chalcogenides such as moly disulfide and tungsten disulfide. Essentially, these are materials which are two-dimensional, layered materials. You can take the powder, produce essentially a suspension through sonication, and if you get everything right, you have actually a very nice and very fine suspension, which you can then take and deposit directly onto the transparent electrode that you're having, the indium tin oxide in this case. So this is exactly what we've done. And we realized actually we could form a very complete layer of these flakes of the 2D material over the ITO surface. It is very difficult to actually see any difference with the atomic force microscope. You see only a few nanometers changes. But when you do the energy, the analysis of the elemental analysis using EDX of the surface, you can start seeing of course, the signs of the indium, which is present in the ITO, but tungsten and molybdenum is not. And when we have these flakes deposited on top of the ITO, we can now start detecting. And what you can see here is that the tungsten is a bit more uniform than the molybdenum. And what we then did, we created devices, and we were very surprised to see that despite the atomic layer thicknesses of these two-dimensional materials and the way we have essentially deposited them on top of ITO by just simple spin coating, we're able to yield devices with, at the time was the maximum, not for the specific combinations, we're able to essentially push the device efficiency to over 17%, especially with NFA materials such as a Y6 combined with the right donors. Essentially, what you see, where the origin of this performance enhancement comes from, is both from the VOC, but also the higher current. The higher current is primarily attributed to change in the photonic structure of these devices. And of course, when we compare with PEDOT-PSS, we have this reduction of the parasitic absorption that PEDOT-PSS has there. Even though it's optimized in terms of thickness, PEDOT-PSS will tend to absorb in the ANIA-IR part of the spectrum there, which is very critical. And as you can see here also, we see change on the way that the entire EQE spectrum actually looks like because of the changes in the photonic structure of our device. Essentially, we're removing a thin film and replacing with an atomically thin, essentially, layer, which does not have the same optical effect on the photonic structure of this cell. So essentially, this is a summary of the HERO devices. We tried with a number of different bulk heterojunction blends, and we're able to demonstrate at the time one of the most efficient devices, OPV devices, back in 2019, reaching a 17% external power conversion efficiency. But the most important is that these materials are nothing special. But although they do deliver the device, preparing the suspensions of a good quality 2D material is not trivial, and even depends on the source of the material. For example, if you use powders of molybdenum disulfide or tungsten disulfide from different suppliers, you may end up with different quality suspension. This was a big problem that we couldn't really solve. So as a result, the producibility is becoming an issue. So this led us to look and search for alternative materials. I personally spent many, many years trying to use self-assembled monolayers as surface energy modifiers, either to enable the processing of certain materials, so essentially you increase or you decrease the surface energetics of a surface, or you're trying to improve the injection. But that injection improvement was always emphasized and focused on transistor applications. So here we came across this 2PAC-Z self-assembled monolayer, this carbazole-based self-assembled monolayer that was a magic material and gave a very nice perovskite cell. So we quickly were able to adopt the technology, get the material, apply directly on the ITO, and then create some OPVs. And what we actually discover is that these materials are very easy to functionalize in ITO. Surprise, surprise, not this is very known because the phosphonic acid unit here, which essentially acts as the head group, then we have the tail and the end group. And the beauty of these materials is that the end group can be really modified atom by atom through simple chemistry. The tail, of course, can be follow a similar kind of trend. We can make it longer. And the head group is actually pretty good when it comes down to ITO. Phosphonic acid will be exhibiting a very strong affinity to react with the surface of ITO. And this is a two molecules, two different SAMs, the methoxy and the brominated versions of these 2PAC-Z that we have also studied. So soon realized that replacing just the thick HTL, like the copper thiazide or the PEDOT-PSS, with this monolayer HTL, we're able to deliver to achieve OPVs with a power conversion efficiency of 18%. And as you can see, it's not just the efficiency, overall efficiency. We gain current as compared, of course, to PEDOT-PSS. This is not surprising because we're suppressing that parasitic absorption. You can see how the current increase across the EQ spectrum, but we also improve the stability of these devices. This is a very hot topic right now because there is, and including data from our laboratory that shows, depending the bulk heterojunction system you're using and the specific SAM, the stability can be improved or actually degrade. So these self-assembled monolayers appear to be impacting not just the energetic of the interface in the case of organic solar cells, but also the morphology of the bulk heterojunction we're getting at. So this is how important and how big the impact is on the optical properties of the electrode. So essentially, we're comparing here these two self-assembled monolayers functionalized directly on ITO against the PSS ITO electrode, and we can see all this parasitic absorption can be suppressed by simply switching to this self-assembled monolayer. Of course, meaning that we removing this parasitic absorption doesn't mean we gain, because it all comes down to how we photonically structure a device. So we can play with other parameters to compensate for that parasitic absorption. And this is what often we are doing for the case of PSS-based solar cells. But nevertheless, shows that we are now dealing with monolayer systems where we can start tuning atom by atom the periphery of that molecule and making a huge impact on the performance of the devices. Such a control over an interface we never had before. We were always relying on thin solid films where we knew very little. We know very little about the surface properties of PSS because it's not really a structured material. We don't see a very regular pattern. Now we have essentially a self-assembled monolayer that forms and interact with specific sites on the surface of that ITO electrode. The challenge now is to understand what exactly and what is important in this interaction. We're working intensively on this topic as we speak. We also can change the conjugated unit from carbons to something else. Here is staying with the 2PAC-Z, and I show two examples again with the brominated and the methoxy groups 2PAC-Z versions, and you can see the electron wave function delocalization is very different depending what these end groups are, and we see essentially these tiny chemical changes on the periphery of the carbazole can change the work function dramatically. So in one case, we have the brominated version where it's actually push the work function to 4.7 or so electron volts of ITO. And this one here, which essentially increases it moderately to 5.3. Of course, this is just what we see with a Kelvin probe. We don't really know what happened when we create a bulk heterojunction ITO sum interface, because we have a number of pinning effects that, of course, play a major role at the overall electronic landscape across that interface. Nevertheless, the impact is dramatic. On one hand, we have essentially the PSS, which is heavily optimized devices and give us very good efficiencies, typically 17.5%, some of the highest. And then we change with the different sums. This one, the green line, you can see that you're losing a lot in the VOC. Perhaps the work function relation is dramatic. And we see a kind of a linear scaling between the work function of some modified ITO electrodes and the overall VOC, which is very, very encouraging. But the moment we have the brominated version, essentially we have a much stronger dipole, we have a much deeper work function of the electrode, and a much more favorable interface between the bulk heterojunction and that ITO functionalized with a sum electrode. And essentially this allowed to demonstrate OPVs with efficiency of 18.4%. What one of the most interesting findings from that study is actually we can take these devices now, which are highly efficient, over 18%, use them, and then reclaim part of the device, and specifically reclaim the ITO substrate part. How do we do that? We dip the whole device in chloroform, we remove the organic and the top layer, then we soak in water and bath to remove the PSS, IPA bath to clean all the residues, oxygen plasma to burn away any organics, including the self-assembled monolayer. And then we take that plastic or glass ITO substrate, refunctionalize a new sum, deposit the bulk heterojunction and complete the device fabrication, test it. And essentially what we discover is that when we're using sums instead of PSS, we can actually do this several times without a drop in the overall efficiency between reclaim and reuse steps. While in the case of PDOT, the device is only under 3 cycles of reclaim and reuse drop dramatically without possibility to recover the original performance. This is clearly not the case with the SAMs, because the performance of the SAMs actually remain the same. So essentially, that's an interesting finding we did not expect. In a way, it was kind of be derived from basic knowledge we have. We know PWPSS is very acidic, reacts with ITO, and changes its surface chemistry, therefore changes the electrostatic across the interface. So the moment we replace that PWPSS, we're essentially damaging that surface of ITO permanently without being able to replenish the original or recover the original properties. And this is some of the latest data that is been submitted recently. What you see here, you see a number of other self-assembled monolayers where essentially we start changing the periphery of these SAMs, and we see essentially a dramatic impact also on the overall performance. Now we're at a point where we're very close to 19%, but most importantly, we see that there's a big difference in statistical distribution of the performance of the devices the moment we shift from PWPSS to some functionalized surfaces. And you see the chlorine-based 2PAC-Z is one of the hero SAMs we have right now, and appears to give the best results with specific organic bulk heterojunction systems. So my belief personally is that some interlayers are here to stay, and I believe will provide solutions which are very important for the field of OPV in general. More recently, and we published it I think a few weeks ago, we were able to use the same SAMs for creating Hall injecting layers for highly efficient perovskite light-emitting diodes, essentially replacing altogether PWPSS. And we saw by replacing it with a self-assembled monolayer Hall injecting layer, we're able to improve the efficiency of these perovskite LEDs quite a lot. And finally, the last part of my talk for the remaining 4 or 5 minutes, I'd like to cover a little bit about the multifunctional additives, specifically electronic additives, directly into the bulk heterojunction of OPVs, and how these additives can improve the overall performance of these cells. So this study started from my passion on doping from the very early days of my research career. In my PhD, I was looking at the doping of oxygen of organic solar cells. That started before 2000. Let me tell you that. The first paper I published was 2003 on oxygen doping effects on the performance of Schottky type solar cells based on phthalocyanine. And now we had the emergence of these NFAs, and from the work we've been doing on field effect transistor, we realized a lot of these NFAs suffer in terms of electron transport due to traps. So we thought of actually introducing some N-type dopants and improve the charge transporting characteristics. And indeed, we were able to do that and reported this effect in a number of studies. Then this led to a kind of an idea of why don't we try to use the dopant directly on the bulk heterojunction. Many groups in the past have attempted this with P-type as well as N-type dopants, but always the success was very moderate, if any success at all. So what we did in our case, we took some of the state-of-the-art bulk heterojunction materials, and we started screening a number of dopants. At the time, we'd been working on this benzyl vialogen, BV, a known N-type dopant in the organic and inorganic world. So essentially, we took small amounts of it, we introduced it directly into the formulation of our bulk heterojunction and spin coated it on top of the ITO electrodes. Before we essentially make the devices, we realized that we see an N-doping effect. We see what appear to be a generation of free electrons because of the presence of the BV, but we also have seen an enhanced absorption across the layer. It appears as if the layers were getting more dense, if you know what I mean. And indeed, when we look down on these bulk heterojunction layers without dopant here on the left, all the way to doped systems here on the right, this is the different coloration just to highlight the differences. What we essentially see, and we take these images and convert them to histograms, we see that upon optimal doping concentration, we see a shift of the histogram towards zero height, which means essentially the layer becomes flatter. Or in other words, if it's the same thickness, will become more dense, grams per unit volume. That's essentially justify the increase in this absorption coefficient that we've been observing across many different bulk heterojunction systems. Indeed, when we made the devices, we realized that minute amounts of this dopant present in the bulk heterojunction, 0.004 weight percent, can increase the short circuit current quite a lot, and essentially lead to dramatic changes in the aqueous spectral shape. You see different features being enhanced because of the changes in the optical properties of that essentially bulk heterojunction layer. And of course, the combined effect of better electron transporting, which is also evidenced from our data, and the improved quality of the bulk heterojunction, potentially phase separation of the donor and acceptor components, led to these very interesting devices, which are more stable in terms of operational stability, but much more efficient. So essentially, what we've been able to show with this BV N-type doping device, we show essentially OPVs with an efficiency of 17.1%. Since then, we've been, of course, expanding this work, and we extended to a number of bulk heterojunctions, and we show that essentially BV is a generic, it's a universal dopant, and appears to have a positive effect for a lot of relevant bulk heterojunction systems. Another example, which we discovered a few years later, was essentially the D-quad. This is a commercially available material. It comes in a salt form. You have to separate the neutral D-quad, add it in your bulk heterojunction, and we saw essentially this D-quad playing a major role as a microstructure modifier, as well as a moderate dopant. So making devices, we saw that we can enhance the EQE across the spectrum at different parts of the electromagnetic spectrum. So essentially this green highlighted region shows where the gain is coming from for the current we observe in this GAV curve under standard 1 sun illumination, and essentially allow us to reach an efficiency of 18.3%. So this paper was published a few years back. Since then, we've been able to essentially, before I finish, we've been able to combine doping with other interlayer technologies and push this efficiency even further. I can't talk about that work right now, but this is essentially where we are today. And with that, I just want to summarize the topics I have covered. I hope I introduced this copper thiocyanate system and how interesting it is, and the ability to essentially electronically improve the quality by doping. Chlorine doping is the most successful approach we have identified so far. Also, the low-dimensional interlayers. The most important technology for me today is probably the self-assembled monolayers. I think SAMs are here to stay. There is a lot of unknowns related to the SAM-based OPVs. We believe and we have evidence that the SAM is responsible for, of course, affecting the morphology of the bulk heterojunction, but also the phase separation within that bulk heterojunction after the device fabrication and during operation under different conditions. So we are trying to understand how we actually use this power of SAMs to stabilize or even improve the performance of OPVs. And finally, the N-type dopants, which open up a whole of new opportunities. Essentially, these N-type dopants is nothing more like the salt and pepper of OPVs. This is how I view it. You put a little bit and essentially fix a lot of the problems that comes with the OPVs. And there's a lot of work to be done. We are combining now a lot of these elements with new ideas, and we see there is still room for improvement, essentially pushing already state-of-the-art materials towards the intrinsic ultimate performance limits, which we see there's still room for getting better data. And with this, I'd like to also acknowledge the contribution of the various groups around the world and my team for contributing and, of course, making the difference in all these projects, and also to thank you for your attention. Thank you.
Thank you, Thomas, for this wonderful talk. I don't have many questions, but let's see the audience here. Our first, Marcelo, can you show the question? I think it's from Albert Bittencourt. He's congratulations for your research, and please comment on the durability and lifetime of the OPV devices. Also, I have a comment on that, Thomas. This lifetime that you mentioned, like that is higher than 10 years. There's always a discussion that I have also with Diego. This is for indoor applications, right? Can you?
Yeah, the indoor application, I think this is an area which will explode in the coming 10 years. I think there is a genuine need for power sources. It's not power generation, but powering this plethora of devices that we'll see emerging, whether it's going to be a sensor, an autonomous sensor, which is located in a fixed position and then powers itself and transmits some sort of information. And there's a lot of application like that. And currently there is no solution how to power them. Having a battery is not necessarily a good, of course, battery might be part of the solution, but delivering there a solution which is better than silicon, I think is well within reach using organic PVs or perovskites. I think I put them in the same category. I do see there are a lot of opportunities when it comes down to commercialization of these technologies.
Okay, our next question is from Aguinaldo. Aguinaldo is asking you for the excellent results with copper to cyanide in perovskite. So what are some of the drawbacks in terms of device stability when rely on aqueous ammonia as a solvent for this whole transport material?
Yeah, the ammonia, so essentially is an aqueous ammonia. So we have a small percentage of ammonia in there, but of course we end up, the problem with copper thiocyanate, it's one of the polycrystalline materials that we end up with a lot of defects. And this is where chlorine comes and interacts with, if you're interested, you can read that paper we just published, interacts with the copper atoms and essentially appears to induce this effective p-doping, but essentially it's like fixing the problems of a polycrystalline material. The other problem is that although we can make perovskites, perovskites tend to react. A lot of the perovskites and solvent tend to react with copper thiocyanate. So there is also that part of the issue. There are ways around it, but a lot of the perovskite, high-performing perovskites will struggle with copper thiocyanate. And this is one of the reasons why I think it hasn't really picked up. But there are ways around. We have found solutions, for example, how we can combine copper thiocyanate with other elements to improve the overall performance. But copper thiocyanate remains a polycrystalline material. So if you were to ask me if I was to pick up a technology, the self-assembled monolayers is the ultimate technology. There is nothing simpler than that. And we've been using in my group SAMs based on phosphonic acids for creating nanodielectrics. So creating nanodielectric for transistor is not an easy thing. One few molecules missing and you have a pinhole. And we've been able to make this nanodielectric. We're not the ones that we pioneered. Professor Hagen Klauk from Max Planck in Germany were the first to publish these dielectrics. But this tells you how reproducible and how robust this self-assembly process can be. And I think if we can push the technology, identify even better, more functional SAMs, will be great, because will not only increase the performance, but actually will simplify the manufacturability of the devices.
No, I do believe. I think SAM is there. It's going to stay there. And back into this copper thiocyanate, my question is, because it's copper 1, right? The oxidation state. So how is about the oxidation to copper 2? Because do have to anneal this before depositing the OPV layer or the perovskite? So how is this ability copper 1 to 2?
Yes, so we do anneal, and essentially we have non-stoichiometric system in place. The chemistry is not perfect, and I think part of the aqueous ammonia solution is because probably we end up with a little bit more better quality material in place in terms of the chemistry we do. But copper thiocyanate, including the from experiment, but also the theoretical work we've done, the copper and the the non-stoichiometric species there, they are quite mobile. So essentially we have copper atoms moving around and about. So essentially are not the most stable system we would like to have in place. And I think this is the ultimate bottleneck of this material. For us, we started with copper thiocyanate, and we were hoping to identify a similar system from that pseudo-halide family of materials, but copper thiocyanate remained the best. Sadly, we couldn't identify a better one. Yeah.
Even if you compare with your the other 2D materials that you showed today, is just molybdenum sulfide and tungstenium sulfide. When you even when you compare with those, do you think it's still better?
Yes, so those were essentially quite a surprise. We don't expect to see such a high results, good efficiency cells. We are so suspicious that whether we have the flakes or not there, that we are even analyzing the solvents alone, making cells, and essentially the 2D material is there. They can yield as good devices as the copper thiocyanate, a little bit better. I think it has to do with the compatibility of the bulk heterojunction and the interface. Essentially, with the 2D materials, we see a planarization effect happening and some specific interaction that prevail and make that interface very good. However, the problem is that how do you prepare these two-dimensional suspensions? We always had this variability, and we are not experts in preparing 2D materials. We learn a lot by doing that. But
that's my question. How do you grow then? Do you grow from solution, or you're doing like some CVD? How you prepare them?
It is a solution exfoliated using a sonication technique. It's just a standard approaches that people reported in the past, a number of groups around the world. We didn't invent anything there. Essentially, you end up in every process, not every process, but the process can be very similar, but every batch of material can give you slightly different results. That was the biggest obstacle we have faced.
Okay, let me stop talking, but I have one more question here on our chat. Mohamed Ali, can you comment on large scalability of the perovskite solar cells? Where do we stand now?
Yeah.
Especially because Oxford PV, I remember last time that I checked the website, it was still announcing for 2022. So Thomas, you are close to them. Tell us, there's some spoiler on this.
No, I mean, Henry Snaith is a very good friend of mine, and I was the examiner of his first perovskite student, who discovered this. Yeah, Mike Lee, and Henry was always telling me that the next year we're going to have the first product. Yeah, I hope they will have the first product. I really do. I think it's going to be a success for everyone. We don't do a large area processing. I don't think we are good at doing anything large in my lab, but we definitely work with the right people to explore the possibility. For me, organic and perovskites are very, very close to each other. I think identifying solution for one helps the other, and as you can see, a lot of the interlayer and the cross-breeding between the technologies is happening already. So essentially, we see a lot of similar technology being applied on both families of PV. Now, how we process the perovskite in larger area, perovskites are notorious, are very difficult to control the crystallization kinetics. And this is the two differences. There is a main difference, I think, with the OPV technology. In the OPV, we see a clear trend between the electronic properties of the SAM-ITO interface, the energetics, and the performance of the cell. In perovskite, this does not exist at all, to my knowledge. Everything we've done depends on how this SAM affects the crystallization kinetics of the perovskite, not necessarily the energetics of the interface. And that's quite shocking. So essentially, we see very strong effects, but one depends more on the morphology. You end up with a subsequent process layer, perovskite, while the OPVs is not as sensitive to that, because it depends on other processes, on the formation of the phase-separated domains within the bulk heterojunction. And that's very interesting. And I think understanding these fundamental differences and processes will help us to push the efficiency of both families even further, or at least eliminate these losses that we see happening at those interfaces.
You just mentioned a really important that's something that we are focusing now, Thomas, because in our papers in the past, we focus on studying this in situ crystallization in small size devices using the series here, our synchrotron facilities. So it's going to be a challenge for us now to see this crystallization in large scale. Of course, we have a problem to fit our equipment on the beam line, but this is something I think it's for my students that are listening to now, I think it's really a hot topic to try to see the crystallization and really at large scale, because definitely it's totally different from like small devices.
Anna Flavia, you're absolutely spot on. I think we can send you some ITO treated with different sums where we see very big differences, and see whether there are the big differences in the crystallization kinetics between the systems. Yeah. Yeah, and this is, I think, a fantastic experiments. I have to emphasize here, we never had this ability to control an interface energetics by atom and see such a big effect on the macroscopic device. The sums allow exactly that. And I think we never had that before. And I'm quite excited with that ability from my side.
Definitely we need to talk. I think we have a guest here on the studio, Diego.
All right.
Diego that just joined us. Marcelo, did Diego open his camera?
Yeah, yes. I'm sorry, but I'm in the car.
Nice to see you, Diego. Diego, do you have a question to? I think he's no, he's back again.
It's a car internet.
Yeah, it's a car internet. Diego, would you like to?
Yeah.
To ask,
do you hear me? Do you hear me now?
To Thomas. Yes. Go ahead.
Yeah. What was just a couple of questions. One for OPV, another for the perovskite. Interesting your additive, and everybody know that's one of the issue for the scale up and to have a really high efficiency of OPV is to using the new material, and so the new fuller. But it's also true that the higher cost of the synthesis affect this kind of scale up. So do you believe that maybe the use of this additive can compensate the higher cost, and so maybe to reduce the complexity of the donor polymer and the non-fuller, and in order to have something more viable for the market?
Yeah, that's a very good question, Diego. I think I don't think we will be able to compensate for the for the big complexity some of the NFAs present. We cannot really reduce that, or we cannot make the less complex to synthesize material so good. But definitely, I believe that we will soon find NFAs that will be easier to make. Not necessarily will be a Y6 derivative. It will be so sad if we stick with the Y6 for another 10 years in the OPV community. And I do believe in this discovery, and I think there is no reason why I shouldn't expect any development there. And we will always be there, I think, with these additives to broaden that window and essentially of processing and essentially accessing the best performance much easier. I think you can still access the performance we're getting with the additives if you are able to process the layer in an ideal way. But these additives appear to get you there much easier through just simple processing without really need to optimize your processing windows. This is, I think, the process of additives. There might be more fundamental reasons. We see a very strong interaction between these additives and certain components of the bulk heterojunction. Maybe this is something unique. We have not an absolute answer, but it looks like it may not just be an electronic additive that makes screen some traps, but it's actually a much more complicated process that leads to these positive effects. Many things to be discovered, in my view.
Yeah, great. And just Anna, just a really quick question about the perovskite. Everybody know about, and you explain absolutely well, the use of the self-assembly monolayer, and so the benefit that can do. But in the other side, I'm pretty afraid about to using organic material, especially like a first layer in a PIN structure like we are using. And so will be maybe the first layer that is, so if it's not protected by the ultraviolet, will be one of the part that maybe in the fresh sample module or cell give a good benefit, but maybe for the lifetime, so maybe there are some issue or some, maybe not in the intrinsic material, but maybe in the interface or something that can change the performance and so in the end the stability.
Yeah, you're right. There are a lot of unknowns here with the use of these SAMs. We are essentially having systems that work much better than pure PSS. We are having a bulk heterojunction system that really degrade fast when the SAM is present. Although we start with a very high efficiency to degrade rapidly. And there's a lot of discussion in the community. Is this the SAM degradation? I don't think it's the SAM degradation. There's a lot of processes. One is a phase-driven separation by that interface. We've seen this with the P3HD PCBM versions, where we see the interface can actually pin or affect that phase separation. And again, there is no a lot of answers. And now the problem is that we don't have PCBM only. We have all these different NFAs and different donor polymers. So every system appears to be slightly different. I think I don't see personally a dramatic. The chemist may tell me, oh no, these SAMs will be chemically unstable. But when it comes down to UV stability and everything, I don't see a fundamental problem. I see opportunities for SAMs to be pretty stable and remain there during device operation and improve the device operation as well. Of course, this is my gut feeling. I don't have solid evidence. We are on that process, really going deep into the reliability analysis and trying to separate the interface from what happened in the bulk heterojunction. This is not a trivial matter right now. To me, it's not clear what in certain systems causes degradation, and while in the system work quite well. We're also working on inverted cells, and this is an interesting effect, and you can see how potentially that may change also. I know, for example, most of the commercial products, they rely on inverted cell, OPV cell, that's another complexity we're trying to address. But if we understand what essentially drives the degradation in the SAM-based OPVs, I think we will be able to learn a lot how to stabilize also the devices.
Excellent. Thanks, Thomas.
Thank you, Diego.
Thank you, Diego. With that, I'd like to thank you, Thomas, again for this amazing talk. Hope to catch you up in Boston soon. Thank you, Diego, for also joining us from your car.
Okay. Thank you for.
Yeah, thank you for having me here.
No, that's true. So, Diego, Thomas told that he's coming to Brazil in the beginning of next year. So just
we have to arrange it, Diego. We have to arrange it in the next meeting.
Yeah.
Absolutely.
So
Excellent.
with that, I also would like to thank our audience and Agnaldo Marcelo that are working here on backstage. And thank you, and see you in the next Cine webinar. Bye-bye. Are we